Welcome to my Commander X16 programming tutorial series on the Retro Lemur channel. I go by the name Mooing Lemur, and this video is an introduction to 65CO2 assembly language in the context of the Commander X16. Links to playlists for the entire tutorial series can also be found in the description, and I recommend bookmarking one of those playlists. This video contains only explanations, and we won't be writing any full programs in this one. However, if you haven't watched episode 0 and set up your development environment accordingly, I recommend doing so before continuing beyond this episode. In this video, we will be going over the following. We'll cover the overall memory layout of the stock first-generation Commander X16 computer. We'll then go over the registers available on the 65CO2 CPU, followed by all of the available instructions on the 65CO2. Next, an overview of all of the addressing modes and which instructions can use each one. And finally, we'll show an animated illustration of a small assembly language program. Feel free to pause the video or rewind if you need to, as some parts of the tutorial will likely go by quickly. For anyone who's new to assembly language development, much of the video is likely to go over your head the first time you watch it. That's okay. In fact, none of the other videos in the series will require you to watch this one, but I do recommend you watch this one through anyway. You'll almost certainly pick up a few useful nuggets of knowledge. Captions are available on all of the videos in this series. The base Commander X16 system is an 8-bit computer with a 65CO2 processor, just under 40K of main RAM, also known as low RAM, 512K of high RAM, also known as banked RAM, expandable to 2 megabytes, and 512K of ROM. The total address space available to the 65CO2 processor is 64K, or 65,536 bytes. And we need to have a way to reach all of the addressable RAM and ROM within that 64K. We do this with banking. The first 40K of address space is the fixed region, which contains the main RAM, a couple of banking registers, and the addresses for accessing devices, such as the display, keyboard, sound, SD card, etc. Next up, there is a fixed 8K window of address space that we can attach a region of high RAM to. Accessing this part of memory always talks to somewhere in high RAM, and we can control which part of it that is exposed via a special hardware register at address 0. We call each 8K region a bank. Here's an illustration of some assembly language code that manipulates the RAM bank registers and ultimately transfers a byte in memory from one bank to another. Some of the CPU registers are shown at the top of the screen. We'll go over those in detail a little bit later in the video. First, we load the number 5 into the A register. Then we store the contents of the A register into memory address 0. This switches the active RAM bank to bank 5. Next, we load the value from memory address A1000 hex into the X register, which just happens to be 7F hex in this example. Now we load the number 20 hex into the A register. Then we store the contents of the A register into memory address 0. This switches the active RAM bank to bank 20 hex. Note that the value shown to be in A1000 has changed, as that whole region of address space points to RAM bank 20 now instead of bank 5. And finally, we store the value from the X register into memory address A1000. There is also a fixed 16K window of address space that we can attach a region of ROM to, and we can control this region via hardware register at address 1. We also call each 16K ROM region a bank. Here's another illustration of some assembly language code. This time we're going to load some values out of various ROM banks into the 3 CPU registers. First, we load the value 1 into the A register. Next, we store the value from the A register into memory address 1. This switches the active ROM bank to bank 1. Then we load the value from memory location C1000 into the A register. Now we increment the value in memory location 1, which switches the active ROM bank to bank 2. And then we load the value from memory location C1000 in this new bank into the X register. Again, we increment the value in memory location 1, which switches the active ROM bank to bank 3. Finally, we load the value from memory location C1000 into the Y register. This was kind of a contrived example, and the values stored in the actual ROM won't be these exact values, but I did want to use this demonstration to show how addresses in the banked areas of the address space connect to different banks, and an example of how you can control that in code. The fixed RAM region on the Commander X16 is arranged into the following regions. Addresses 0 and 1 are known as the RAM bank and ROM bank registers respectively. They are addresses in RAM, but they also control the banking logic on the motherboard. Addresses 2 through 21 hex are set aside for parameter passing to certain kernel functions, but they're also available to user programs. 22 through 7F are dedicated to user programs. 80 through FF are used by the kernel and BASIC, including the floating point math library. The range 100 through 1FF is used for the CPU stack. 200 through 3FF is used by the kernel and BASIC for a lot of different things, including trampolines for handling interrupts and for jumping between ROM banks, as well as vectors for replacing the default behaviors of certain API calls. 400 through 7FF is free for the user to use. 800 all the way through 9EFF is the main program space, with the value at 800 set to 0 to allow BASIC to run. A typical user program starts at address 801 hex, whether it was written in BASIC, Assembly Language, or another supported language. The vast majority of non-BASIC programs will still begin with a very small BASIC program that jumps to the first machine language instruction, making them easy to launch. The rest of the main program space, not used by the loaded program, is typically used for variables, or whatever the user program wants to use it for. And finally, 9F00 through 9FFF is the I/O range. Unlike the rest of the memory map, which talks to RAM or ROM, this region talks to onboard and peripheral devices. This includes a VIA 65C22 chip, which is connected to the SNES controller ports, the IEC disk drive port, and the I2C bus. I2C is used to talk to the System Management Controller, or SMC, and the real-time clock. The SMC connection is used mainly for keyboard and mouse input. An optional second VIA connects to the user port header on the motherboard. We then have the VIRA and all of its registers, for instance, for changing display modes, writing to video RAM, playing sound, or reading and writing to the SD card. Next is the onboard Yamaha FM chip, and the rest of the I/O space is available for expansion cards. Before we move on, you may have noticed the spelling KERNAL in this video, and potentially other sources. This spelling was used in the technical documentation for the Commodore 8-bit series of computers, and eventually became the official name of their kernel. Since the Commander X16's kernel is based on the Commodore 64 kernel and shares much of its API, this spelling is also used for the name of the Commander X16's kernel implementation. In high RAM, the first 8K bank is reserved for the system and is used for storing more kernel state, such as the active keyboard layout, buffers, and state for the FAT32 driver, and other state that there isn't room for in the main RAM. All of the remaining banks in high RAM are available to user programs. The onboard ROM has a capacity of 32 banks, totaling 512 kilobytes. As of ROM version R48, the bank layout looks like this for banks up to 0F hex. ROM banks 20 hex and higher can be mapped by an expansion card or cartridge, but do not connect to anything on a stock system. Most programs normally do not need to manually change the ROM bank. Built-in function calls will usually handle all of that themselves, but there are some instances where we may want to set the ROM bank explicitly. We'll cover those in a later video. These are the registers that we can manipulate directly on the 65CO2 CPU. First, we have the A register, or accumulator. This is the most flexible one. It is used for math operations as well as general loads and stores. Next, we have the X and Y registers. They don't support mathematical operations, but they can hold values temporarily or function as indexes, or in other words, offsets to addresses in memory. They also support loads and stores just like the accumulator. Next, the flags register, also called P, made up of 8 individual bits. There are 4 bits of the register that respond based on the result of loads, compares, and arithmetic or logic operations. This bit reflects whether the CPU is in decimal mode. This bit, when set, is used to prevent IRQ interrupts, and the remaining 2 bits are not part of the hardware flags register, but this one has a meaning only when it is pushed to the stack as part of a BRK or IRQ interrupt. We'll cover the details in another video. All 4 of these registers, A, X, Y, and P, support having their contents pushed onto or pulled from the stack. Next, the stack pointer. This points to the next location available on the stack that a push operation will write to. The stack pointer is 8 bits, but has an applied base address of 100 hex. So its possible range of values is actually 100 to 1FF hex. The stack is written from the top of memory downward, so a totally empty stack has the stack pointer set to FF hex. And finally, the program counter, which is the only 16-bit register. It points to the location in memory of the instruction to be executed. On other CPUs, this is often called the instruction pointer. It normally ticks forward as instructions are read from memory and can be changed via branch or jump instructions. Here, we will go over all of the instructions available on the 65C02. This part of the tutorial will cover all of the instructions available, but it will move fairly quickly. I don't expect anyone learning about the CPU for the first time to understand everything explained in this section, as it's a lot to absorb in one go. Don't worry, you won't need to memorize all of this in order to follow along with the rest of the tutorial series, as we will reintroduce each instruction the first time that we use it. First, the load instructions. LDA, LDX, and LDY all read a value from memory into the respective register. This can be from an arbitrary memory location or from program code in memory in the form of an immediate value. Now the store instructions. STA, STX, STY, and STZ all put a value into memory. The first three of these store the value into memory from the corresponding register, and the final one stores the value 0 into memory. Next, the transfer instructions. These copy values from one register to another. TAX, TAY, TXA, and TYA all transfer a value between the accumulator and the index registers. TXS and TSX transfer a value between the X register and the stack pointer. You can see in this example how the stack pointer moves during a TXS instruction. Now, the stack instructions. These affect registers in a similar way to the load and store instructions, but instead of arbitrary memory, they always use memory pointed to by the stack pointer. PHA, PHP, PHX, and PHY are the push instructions. They all transfer a value from the corresponding register into memory pointed to by the stack pointer, and then decrement the pointer. The stack is filled from the top down. When executing a PHP instruction, the two unused bits of the flags register end up being pushed as ones. PLA, PLP, PLX, and PLY are the pull or pop instructions. They all transfer a value from the stack to the corresponding register. First, the stack pointer is incremented, then the value is copied into the register. Normally, you would pull values off the stack in reverse order to how you push them on. In other words, last in, first out. In this demonstration, we didn't do that. This allowed us to swap the values between X and Y. Next, the increment and decrement instructions. These will raise or lower the value of a register or memory by 1. INX and INY increase the value of the corresponding register by 1. DEX and DEY decrease the value of the corresponding register by 1. INC and DEC can be used on memory without having to load it into a register first. INC and DEC can also modify the A register. You can use any of these three forms of the instruction for that. They're all equivalent to each other. I usually use the first one. Next, the arithmetic and compare operations. We're going to jump ahead a little and introduce some instructions that affect flags. CLC will clear or turn off the carry flag bit. The ADC or add with carry instruction adds a value in memory to the value in the accumulator and stores the result in the accumulator. If the carry bit in the flags register is set, 1 is added to the result. SEC will set or turn on the carry flag bit. The SBC, or subtract with carry instruction, subtracts a value in memory from the value in the accumulator and stores the result in the accumulator. If the carry bit in the flags register is clear or not set, 1 is additionally subtracted. The carry flag is treated as an inverted borrow flag. The carry behavior for ADC and SBC is useful for doing arithmetic on numbers larger than 8 bits. CMP, CPX, and CPY are the compare instructions for the A, X, and Y registers respectively. Internally, they're implemented as subtraction instructions. However, they only affect the flags register rather than storing the result of the subtraction, and they implicitly set the carry bit before doing the subtraction. This behavior is useful when using them in combination with branch instructions. Branching on the 65C02 processor is a way to control program flow, and each branch instruction looks at one of the flags register bits. A branch target can be up to 128 bytes earlier in memory than the current program counter, or up to 127 bytes later. The branch instructions behave like conditional go-tos in combination with compare instructions. BCS will branch if the carry bit is set. After a compare instruction, this functionally means branch if the register value is greater than or equal to the value in memory. BCC is its logical opposite, branch if carry is clear. It functionally means branch if the register value is less than the value in memory. BEQ will branch if the 0 bit is set. After a compare instruction, this means branch if the register value is equal to the value in memory. But we can also use it to test for whether the last operation resulted in 0, as we're doing in this example with BNE. BNE is BEQ's logical opposite, branch if the 0 bit is clear, or after a compare instruction, branch if not equal. In this example, we're using the BNE instruction to test the X register after the DEX instruction. If it is non-zero, we branch to the loop label and repeat the loop. When it finally reaches 0, we no longer branch. BMI, or branch on minus, will branch if the negative flag is set. This can happen whenever the result of a compare operation is a value between 80 hex and FF hex inclusive. Or we can test a load and branch if the most significant bit of the result is set. BPL is BMI's logical opposite, branch on plus. This will branch if the negative flag is clear. This time we're using it in a loop condition. Instead of branching when x is not 0, we're branching until we go past 0. These 6 branch instructions are useful after compares, as well as after operations other than compares, which modify flags. All of these instructions affect one or more of these 3 flags. The next 2 branch instructions are based on the value of the overflow bit in the flags register. BVS will branch if the overflow bit is set, and BVC will branch if the overflow bit is clear. The overflow flag is only ever affected by these 6 instructions, and it is mainly useful in signed arithmetic operations to discover whether a value overflowed from positive to negative or vice versa. And finally, we have BRA, which is branch always. Next, the control instructions. JMP is the jump instruction. A jump is similar to a branch, but unlike a branch, its target can be anywhere inside the 64K address space. JSR is jump to subroutine. This instruction will save the current PC onto the stack, specifically the address of the final byte of the instruction operand, then jump to the target address. RTS is the return from subroutine instruction. It will pull 2 bytes off the stack to populate the program counter, then continue execution after incrementing the program counter. BRK is the break instruction. It triggers the processor to behave somewhat like an interrupt was triggered. We'll go over the exact behavior in another video. And RTI is the return from interrupt instruction. We'll also cover this, along with how interrupts work, in another video. 4 of the flag bits can be controlled via these 7 instructions. SED sets the decimal flag, and as already introduced earlier, SEC sets the carry flag. Decimal mode changes how the ADC and SBC instructions behave, allowing the programmer to use a byte to perform math on a 2-digit decimal number with each digit consuming 4 bits, instead of the usual 8-bit value. This is often used to make the math easier for game scoreboards. Also mentioned earlier, CLC clears the carry flag, and CLD clears the decimal flag. SEI and CLI set and clear the interrupt inhibit flag respectively. And finally, CLV clears the overflow flag bit. There is no corresponding SEV instruction. Next, the bit shifting instructions. All of the bit shift operations can operate on memory or the accumulator. ASL, or arithmetic shift left, shifts all bits leftward, shifting a 0 into bit 0, and moves the top bit into carry. ROL, or rotate left, does the same thing as ASL, except it moves the old carry into bit 0 instead of a 0. LSR, or logical shift right, shifts all bits rightward, shifting a 0 into bit 7, and moves the low bit into carry. ROR, or rotate right, does the same thing as LSR, except it shifts the old carry into bit 7 instead of a 0. The logic instructions consist of 3 instructions that affect the accumulator, 1 that affects only flags, and 2 that affect memory. AND does a logical AND between memory or an immediate value and the accumulator, and then stores the result into the accumulator. ORA does a logical OR between memory or an immediate value and the accumulator, and then stores the result in the accumulator. EOR does a logical exclusive OR between memory or an immediate value and the accumulator, and then stores the result in the accumulator. BIT has two modes. BIT on a memory address does a logical AND between the accumulator and the value at the address, and affects the zero flag based on whether the result is 0. It also affects the negative and overflow flags based on the value of bit 7 and bit 6 in memory respectively, so it is useful for checking a memory address for these two specific bits without needing to load it into a register first. The second mode of BIT is on an immediate value. It affects the 0 flag based on whether a logical AND between the accumulator and the immediate value is 0, but it leaves the negative and overflow flags untouched. TSB, test and set bits, does a logical AND between the accumulator and memory, and sets or clears the 0 flag based on the result. It also does a logical OR between the accumulator and memory, and stores the result in memory. TRB, test and reset bits, does a logical AND between the accumulator and memory, and sets or clears the 0 flag based on the result. It also does a logical AND between a bitwise inversion of the accumulator and memory, and stores the result in memory. We have a few more instructions that don't fit neatly into any category. The WAI instruction waits for an interrupt to be asserted. The jump into the interrupt vector happens first, then RTI will return to the instruction immediately following the WAI. If interrupts are inhibited, WAI will only wait so long as the IRQ line is not asserted. The STP instruction halts the CPU. In the Commander X16 emulator, it can also be used to break into the emulator debugger. On real hardware, the CPU is halted completely until the system is reset. NOP is a no-op instruction. Nothing is affected, and it will continue execution. And finally, we have 4 sets of instructions that are discouraged for use on the Commander X16. All of the instructions that we have introduced so far are supported on the 65C02 and the 65C816. Code written with this in mind will work on the stock 65C02 processor, as well as on Commander X16 systems that support a 65C816. These are the forbidden instructions that only work on the 65C02. RMB0 through RMB7, which clear a single bit at a given 0-page address. SMB0 through SMB7, which set a single bit at a given 0-page address. BBR0 through BBR7, which branch if a specific bit in a given 0-page address is clear. And BBS0 through BBS7, which branch if a specific bit in a given 0-page address is set. In order to write code that works on every Commander X16 system, we will avoid any use of these in the tutorial series. Now on to machine language and addressing modes. An addressing mode is defined as a rule for how the CPU handles an operand for an instruction. For instance, loading a value from a memory address is going to be a different addressing mode from that of loading an immediate value. The addressing mode for each instruction is chosen based on how the assembler parses your source code. The 65C02 processor's machine language opcodes are all 1 byte long. Each opcode represents a combination of the instruction and the addressing mode. For instance, LDA in absolute mode is opcode AD, but LDA in immediate mode is opcode A9. The 65C02 has 15 distinct addressing modes. One of them is used only by the BBR and BBS instructions, so we'll omit that one in this explanation. Here are the remaining 14 addressing modes. Implied mode is when the instruction has no operand at all. The target of the action is, well, implied and doesn't need to be specified. Immediate mode is when the operand is treated as a literal numeric value, usually indicated by the hash symbol. Absolute mode is when the operand is treated as a 16-bit memory address. X-indexed absolute mode uses the value in the X register as an offset to the given 16-bit memory address. Y-indexed absolute mode likewise uses the value in the Y register as an offset to the given 16-bit memory address. Absolute indirect mode uses the contents of 2 adjacent memory addresses, starting at the one given, as a 16-bit pointer to another memory address. X indexed absolute indirect mode is the same as absolute indirect mode, except the value in the X register is added to the given address before extracting the pointer. Zero-page mode uses a 1-byte operand as a memory address pointing within the first page of memory, aptly called the zero page. Because zero-page mode uses one less byte of code than absolute mode, it runs faster, as it doesn't have to spend as many CPU cycles fetching the instructions. It's very useful for code that needs to run as fast as possible. X-indexed zero-page mode uses the value in the X register as an offset to the given zero-page address. If the sum of the given address and X would make the effective address higher than FF, it wraps around to 00 and stays in the zero page. Y-indexed zero-page mode likewise adds the value in the Y register to the given zero-page address to get the effective address. Similarly, it will wrap around to the beginning of the zero page if the effective address were to go past the end. Zero-page indirect mode uses a 2-byte pointer that starts at the given zero-page address as the effective address. X-indexed zero-page indirect mode adds the value in the X register to the given zero-page address, then uses that intermediate address as the beginning of the 2-byte pointer to the effective address. Zero-page indirect Y-index mode uses a 2-byte pointer that starts at the given zero-page address as the intermediate address, then adds the value of the Y register to the pointer contained at that intermediate address to get the effective address. And finally, relative mode is used by the branch instructions as a signed 8-bit memory offset to branch to. When you're writing assembly with branch instructions, you would normally type in the label or address to branch to, but the assembler turns this into a relative offset when assembling. Here's a table of instructions and the addressing modes that are possible for each one. And finally, here's an illustration of a short assembly language program which calculates and writes the first 6 Fibonacci numbers to memory. We could have done this in any number of ways. This version places 2 ones in the first 2 slots of memory starting at 1000 hex. It then generates the next 4 numbers in a loop. With the program finished, we have the first 6 Fibonacci numbers in memory locations 1000 hex through 1005 hex. This concludes this episode, which hopefully has helped you familiarize yourself with the overall memory layout of the Commander X16 and how banking works. We covered the 65CO2 processor registers, its instruction set, and its various addressing modes, and we showed a small but functional assembly language program. Check the description for links to reference resources, as well as links to YouTube playlists for the rest of this tutorial series. Thank you for watching.